Hello all, welcome to the next GOAT seminar. Today we have Tung who's going to be speaking about optimal algorithms for sparse separable convex integer programs.
So thank you for the introduction. So my name is Tung, and this is joint work with Krzysztof Hankenschreuder, Martin Kotetzky, and Asaf Levin. And let us get right into it. So what are we doing? We are studying the integer linear programming problem, which can be very succinctly written as follows. I assume that you all know what integer programming is, so I will not delve into details. But now one extension that we do is integer programming, which is not linear anymore, which you might not know. So I will spend some time there. So here again we have these constraints. Like we have this ax equals b constraint, which you know from integer linear programming or linear programming. Again, we have some lower bounds and upper bounds on the variables. And again, we require that the solution has to be an integer point. But what is new is that we're not optimizing a linear function over the variables, but we're optimizing something called a separable convex function. Meaning, what does that mean? It means that your objective function can be expressed as a sum of n different functions, one for each variable, such that each of those functions is convex on its own. So basically, you can imagine that each of these functions is a parabola in a different dimension. Like one of them, you have one parabola for x1, one of them for x2, and so on and so on. And you optimize the sum of those parabolas. Okay, so that's the image you should have in mind. That's the image I have in mind, which is more often incorrect, but don't worry about that. Okay, so let us continue. So you might know that already integer linear programming is an NP-hard problem. And so this is the GOAT seminar. So what do? We focus on some tractable subclasses of this problem. And the tractable subclasses that we study are so-called block-structured matrices. So what's a block-structured matrix? So here are two prominent examples of a block-structured matrix. On the left, we have something called a multi-stage stochastic matrix. On the right, the threefold matrix. And how do you interpret this image? Well, you can imagine that this gigantic thing is your constraint matrix A. And in each of these rectangles, you can have whatever entries, so between whatever integer entries. And outside of these rectangles, we require that the matrix has zeros. Okay, so that's like, and the threefold matrix is kind of the same thing, but is like a transpose of a multi-stage stochastic matrix. So that's what we're studying. And so is it clear what's a threefold matrix, for an example? Okay, Dushan,
why is it called threefold?
Dushan, why is it called threefold?
Because it looks like three.
It looks like a tree, exactly.
So,
yes.
So the top one is the root, and then the two are in layer one, and then proceed, and it looks like.
Yes. So I was offered some. There's some pens. Oh yeah, but what Dushan says is basically. So I can imagine the explanation of threefold. I have no idea why it's a multi-stage stochastic. I think it's because
stochastic means that it's like there are multiple stages of stochasticity of the process, because there are some stage one decisions that you make.
This is the
first rectangle. That's the first stage of decisions. And on top of that, there is some stochastic decision, which is either one or two others, and there are like multiple stages of this process.
Yeah. So that's why it's called like that. So how do you measure like how much a matrix is multi-stage stochastic, or how much a matrix is threefold? We measure it by a graph measure called the treedepth of the matrix. So for these matrices, you can construct a primal graph where for each column, so each variable you make a vertex in your graph, and you connect two vertices if there exists a constraint in which both of these variables appear in a non-zero manner. So multi-stage stochastic matrices correspond to matrices with small primal treedepth, and threefold matrices correspond to matrices with small dual treedepth. So I explain what primal treedepth is. And for the dual treedepth, you basically take the original matrix, you transpose it, and you do the same construction I described. So again, for each column, you make a a vertex and you connect to vertices, say blah blah blah. This by the same constraint. So, and this is the gold seminars. I don't need to explain what treedepth is. I hope. So very shortly, treedepth measures how similar a graph is to a star. Okay, so tree width measures similarity to a tree. Treedepth measures similarity to a star. Without details, we won't need them.
No. So
yeah?
is this like categorical details?
No. So the dual or you have small primal treedepth. That's like, is that something that's characterized separately outside of this matrix world?
Yeah. You can have treedepth of a graph, I suppose.
No, but okay. I'm confused by the word small primal.
Bounded.
Only bounded.
Small equals bounded.
Bounded.
Small means
And primal?
Primal means
Primal is like primal.
primal means that the vertices are the variables. Dual means that the vertices are the constraints.
I see.
Okay. Okay. Thank you.
And it comes from logic.
Yes.
It's the parameter of the corresponding Greifman graph, if you are familiar with this Greifman graph from logic. That's the same meaning.
Okay.
Cool. So now we know what the parameter we want to study is, kind of. Without further details. So let's talk about state of the art. Well, the state of the art by Eisenbrand et al. Is that integer programming with the separable convex function can be solved in time, which looks like FPT in the largest coefficient of the matrix and the depth, either primal or dual treedepth. Then some factor polynomial in the number of variables appears. Then there's a logarithmic factor in the size of the bounding box in which you're searching for your solution. And then there is some logarithm of f gap, where f gap is like you can imagine is that the upper bound on how far from some initial solution your solution can probably be. This is like so that's the state of the art. And if we focus on integer linear programming, then what we can do is that again we have some FPT, something FPT in the largest coefficient of the matrix and the depth of the matrix. And then you have n times log to the parameter n, and so this we can, from any FPT class, that logarithm to the parameter is FPT basically. So what I'm saying is that this time is basically linear in n. Okay, you just shove this log to the parameter into your parameter, and then you have a linear algorithm. And what's the motivation for our result is that we have a strongly linear algorithm for linear programming or integer linear programming. We have something horrible for integer programming. And is there a strong near-linear time algorithm for integer programming? Okay, that's the motivation. So the motivation should be clear. And the answer is no. Why is that? And so in particular, we claim that this factor log of the size of the box in which you're searching for the variable is necessary by the following information-theoretic argument, so unconditional. So imagine that your f is a separable convex function. So now for each of the variables, you're looking for a separate integer optimum. Okay, so you have your parabola, you're looking for the global minimum. And from information theory, we know that basically the best thing you can do is ternary search. And that requires, and the number of operations or comparisons you will need to make is the logarithm of the range of the parabola. So if we want to search for the integer minimum of the sum of these convex functions, then you basically need to find a minimum for each of those parabolas separately. And you take all of this together, and you have that the time is log of the bounding box times n, which is the number of variables. So the conclusion is that this logarithmic factor cannot be avoided. Okay. So that's almost seems like we should be at the end of the talk, but but we are kind of optimistic and we want to match the lower bounds if possible. So so in each of these following, so for the rest of this talk, G prime, G double prime, G NA prime is like some computable function which we don't need to necessarily care what it looks like specifically. So our first result is that if our parameter is the primal treedepth, then we have an algorithm which is FPT in the parameters and basically matches the lower bound I showed before. And up to the dependence in the parameters, this is the best possible. Okay. I mean, maybe this function here will be something horrible, I think like triple exponential, but whatever appears outside of the function is the best that we can do. So our result number 2 is that in the case of dual treedepth, we have almost the best possible. So again, we have something FPT in the dual treedepth and the largest coefficient of the matrix. Again, this lower bound of n log n appears, and then there's this extra log n factor that we didn't manage to avoid yet. So there is something I should talk about is that, okay, so here in the lower bound, I promised that there is like a log of u minus l, which is the size of the parabola. But in the theorems that I state, there's also this right-hand side b. And the reason why the b appears is that in the algorithm we design, we require that we are given an initial feasible solution from which we do some search. And if this initial feasible solution is not given, then we need to find it manually, and that incurs an extra factor of log b. And you might say that, okay, so our result is invalid, and that's the end of the talk. But usually in your applications, when you want to solve something by integer programming, so you have some problem, you try to model it as an integer program, you usually have a good idea of what like an initial feasible solution can be. Maybe it's the all zero vector, maybe it's the all infinity vector, or something like that. So you usually have a good idea of what it is. So you can, in your applications, you can avoid this log b factor. So we can so for the rest of the talk, we can forget about the log b. Yeah, and so I will immediately mention a conjecture. We conjecture that this log n actually cannot be avoided. That no matter what you do in the dual treedepth world, you always have this log n factor here. In the paper, we do provide some indirect evidence to that. I mean, I can talk, but yeah. So for details, you have to look into the paper. But yeah, this is the conjecture we have. And again, the dependence on the parameter is not the focus of this work. The focus of this work is whatever lies outside of the FPT factor over there. So any questions towards the result? Okay, so if not, then let us proceed. So it's time for some pictures. So what's the main idea? The main idea is that we do some sort of scaling. So for an example, if you know how to solve network flows, where you, if you know the algorithm where you process the capacities bit by bit, this is basically it in the integer programming language. But if you don't know what it means, don't worry about it. I'll explain everything. So scaling algorithm. So imagine, so we have like two variables, and in integer programming, we are looking for a solution which lies in z to the n. Okay, here is z to the 2 on this slide. So our idea is that, okay, instead of looking in the integer lattice z to the n, let us look at some super sparse version. Okay, so we have, so for this s, you can imagine 2 to the 100 for an example. So we look at a 2 to the 101 z squared lattice. Okay, this is a very sparse lattice. So conceivably, it should be very easy to find a solution because there's like so little points that you can do whatever and you can find a solution. Okay, so that's the idea. So, I'm in this like super sparse lattice, and I find some sort of initial solution. Okay, and now I want to go, and from this solution, I want to somehow walk to the solution of the original lattice. So what do? We started from 2sz. So now I sparsify, or wait, no, I do the opposite of sparsification. I densify, thank you. I densify the lattice. So instead of looking at 2s to the z, I look at which one is s to the z. So basically, I densify, and now I have a bunch more points, right? And here the idea is that okay, maybe we can invent some sort of theorem which says that okay, after this densification process, the optimum solution of the denser lattice lies somewhere nearby this solution. So we want to imagine that such a theorem exists. And if it exists, then we just simply have a small box in which the solution can lie. So and if the box is small, then we can somehow walk to the solution, and that's it. And then once we find a solution in sz squared, then we go to f. Then again, we add this new solution. We go to s half z squared, and we do the same thing, and over and over and over until we arrive back to the original lattice. Okay, so the idea should be very simple. So the only yes.
I mean, it's linear program, integer linear stuff. So I'm not that, I don't know that much. But
yeah, me neither.
So let's say you're at x0, yeah? Yes. Then actually the optimal point might be just next to you, but
okay.
it's too close. You don't see it yet.
Okay.
And so you walk away, by this big jump to x1.
Okay.
Yes, but it's convex.
I mean, yes, the function is convex. So if
there is this assumption.
If the function wasn't convex, we are done. Like there is nothing we can do basically.
So it's guaranteed to work.
I mean, yes. Yes, it is guaranteed to work.
Okay.
Okay. So this is the idea behind the scaling algorithm. Go to the coarse lattice, find a solution, and if you want to go to a slightly denser lattice, we will prove that we only need to look somewhere nearby.
So in your lattice, you just brute force it. There is no.
There is a clever thing because brute force will not be fast enough. I mean, okay, so I'm very vague about how small this box is. Well, in particular, this box is like n-dimensional, right? So if you do brute force, you will have like this n in the exponent. So you need to do something clever, slightly clever, but don't worry. Not too clever, okay? So I'm not here for too clever stuff. Okay, so formally, what did we do? So formally, imagine that you have some sort of instance of integer programming, and now we set beta to be log of this size of the box in which we're searching, +1 with some seals. So the theorem we prove formally is that there exists some sort of integer row or some sort of real number row, which depends only on the constraint matrix, such that if you give me some sort of initial feasible solution of the instance, then I can find the optimum by solving beta many integer programming instances where each of them has a small bounding box. So this u minus L is small. And each of those functions that will appear, and each of those objective functions in those subinstances will be separable convex as well. So that is quite a mouthful. So what's the main point? The main point is that given this fine print, we can solve integer programming by solving log bounding box many integer programming instances with small bounds. Okay, that's the main point. And we hope that solving integer programming with small bounds is somehow easier than solving integer programming in general. I mean, it sounds easier, but who knows, right? But I mean, so far you don't know yet. So a very pressing question is, what is this row that appears everywhere in this slide? It's a function of a, and what is this function exactly? So there is a notion called a conformal proximity bound, which I will only sketch very vaguely what it is because again the details are not that important. So what's conformal proximity bound? So imagine that you have some sort of integer solution. Oh, so you have some sort of integer program, and you have some integer optimum, and you also can take a relaxation of this integer program. So all your variables from integers become reals. And if you have this relaxation, you can also look for an optimum. Let's say you have this x here is the optimum of the relaxation. Okay. So conformal proximity bound basically is the infimum of all possible reals, such that if I look at an integer optimum, any integer optimum, and I look at any optimum of the relaxation, then in the box between them, I can find a new integer optimum that is close to the relaxation. So to summarize, I mean, the takeaway from this slide is that this proximity bound bounds the distance from any optimum of the relaxation to its closest integer optimum. Okay, so if you were to somehow use it algorithmically, you find a real optimum or the optimum of the relaxation, and you know that you only need to look at this whatever coefficient ball to find the integer optimum. Okay, so that's like the point. And so one thing I should say is that you can define this proximity bound for any norm. So here we use the LP norm, but in most of our applications, we will use either the L1 norm or the L infinity norm. So very informally, what is a proximity bound? It measures the distance between the optimum of the integer program and the optimum of its relaxation. That's it. Again, details will not be needed. So what did we prove? So I will just make a notational notational convenience that if I have SIP as the problem, then SIP is basically integer programming where I look for the solution on the S z to the n lattice. Okay, so nothing wild is happening here. And the theorem that we proved is the following. Imagine you have an integer programming instance, and from that instance, you take its S-scaled instance. So we have the same instance, but instead of looking for the solution in z to the n, you look in the lattice S times z to the n, a sparse lattice. Then what we prove is that if I look at the optimum of the original instance, and I look at it, then there exists some sort of optimum in the scaled instance that is at most S+1 times the proximity bound away. And if this, so not too much. And also vice versa. So if I find an optimum in the scaled version, in the scaled lattice, then I can find an optimum in the original lattice. Again, the bound is the same. Okay. And again, it is not immediately clear what this number is. It depends on whether we have primal or dual treedepth, but you can imagine that this number is small for now. Maybe it's like a tower of treedepth, like of height treedepth. Okay, something like that. But bounded by parameters is what we need. So it's time to see a second proof of the day. So in order to, we will need to prove this scaling proximity theorem. We need a lemma which says the following. So imagine you have an integer program and you have a relaxation, and you have z hat, which is the optimum of the integer program. So then I claim that there exists another integer optimum and another optimum of the relaxation, which are close to each other and which are close to the original counterparts with respect to this proximity bound. And I will show you a sketch of a proof by picture. So imagine that here you have z hat. So we are given some sort of integer optimum, and here you have x hat. So you are given some optimum of the relaxation. So from this conformal proximity bound I showed you before, we are guaranteed that there exists this z star, which is at most some PPA away from this x hat. So you need to walk. So from z hat to z star, you walk by some translation, and from z star to x hat, you also walk by some translation. Add some vector. So you basically copy this vector, and you take this g to walk from z hat to some x star. And so now these I claim will be the two solutions that we are looking for. They're in this box, so the bound should be satisfied. They are also lying inside the bounds, the lower bounds, upper bounds of the variable. So these solutions are feasible, this x star and z star, and the optimality will somehow follow from the convexity. So you should imagine that you have a parabola in this dimension and the vertical dimension. So somehow x star and z star will turn out to be optima as well. Okay, so it's a very rough sketch, and a proof by picture. So I'm doing everything that is wrong with with students here, but I was also a student here, so don't worry. So what are we doing? So what we want to do is that we want to bound the distance between an optimum of the integer program and between an optimum of an S-scaled integer program. Okay, and here comes another proof by picture. So picture number one, imagine that you have some integer optimum, and by the lemma I just showed you before in the previous slide, you can find an optimum of the relaxation, which is at most this PPA away. Okay. So now by some hacking, we can imagine that the lemma one also applies if we scale the lattice. So if we are looking for a real solution and the nearest optimum on the Zn lattice was some PPA away, then you can imagine that the nearest optimum on the Sz to the n lattice is at most S times whatever lemma one said before away. Okay. So the optimum, so the closest optimum of the Zn lattice that lies to the relaxation should be at most S times PPA away, because we just scale up the lattice. And now we just need to bash this picture with triangle inequality, and we get the lemma, the proof, the theorem that I wanted. See, this is a triangle inequality for the reals, like you wanted. So so it made a comeback. So this is how we prove the proximity bound. Any questions? So no questions so far. Very good. Oh, and QED. So so what does the scaling algorithm look like? So imagine you're given some sort of feasible solution. So now we just shift the entire instance so that our given initial feasible solution is at the center. So what it means that 0 becomes an initial feasible solution. You just shift the whole instance so that whatever I write there becomes reality. So if I'm looking into this, if the lattice I start with is this 2 to the beta lattice, so it's a very sparse lattice. So if I set beta to be this quantity, then it will also happen that actually the box of the lattice will be so sparse that 0 will become the only feasible solution of the lattice. And like all possible points of the lattice, like 2 to the beta lattice, will lie outside the bounds U and L. Okay, maybe I should. I mean, yes, the picture.
Then what about the constraints ax equals b?
Right. So that's why if I have an initial feasible solution, I can shift the whole instance so that instead of ax equals b, we have ax equals to 0. Okay. So we set x beta to 0, and then we iterate. So for beta minus 1, beta minus 2, and so on. So we will use this x beta to be the initial feasible solution, and now we use this proximity bounds to find a new solution in the 2 to the I lattice, and we solve it. It is not. I mean, the details are not important yet, but we just somehow solve it, and we have a new feasible solution for a dense lattice, and we just keep repeating for beta minus 1, beta minus 2, and so on. And we always make sure that we center the whole integer programming instance at this new solution, so that we, instead of having ax equals b, we have ax equals 0, and everything will be nice. And once we finish with iteration I equals 0, meaning that we are searching in the z to the n lattice, we found the solutions, we output it. So here in the bound I use 3 times rho. And why is it 3 times? Because if I look at a 2i plus 1 scaled instance, then it's actually a 2 scaled instance of this 2 to the I instance. So the difference in density between 2 to the I plus 1 lattice and 2 to the I lattice is only 2. So we plug this 2 into the S plus 1, and that's where the 3 appears. So just a small remark. The number of iterations. So in this algorithm, we need beta many iterations of solving integer programming, but this beta can be actually decreased to beta over rho. So beta over whatever your proximity bound is. And that's it. So I proved. So what did we do? We showed that we can solve integer programming by solving a small amount of integer programming instances with small bounding boxes. That's what we proved. Any questions? Okay, so I have a question. So how do we actually use this algorithm, right? So if we want to use this algorithm, we need to provide two things. We need to provide a proximity bound for this row, and we need to provide a way to solve integer programming instances with small boxes. Okay, so let us proceed. So we start with a primal algorithm. So for algorithm where the primal treedepth is small and the coefficients are also small. So the statement you remember, and let's proceed to the proof. So here we just use very heavy machinery from other papers. So the first result is by Klein and Reuter, which says that there exists some sort of computable function G prime such that the PPA for P equals infinity, so the infinity norm, is bounded by primal treedepth and the largest coefficient. Okay, so this is a result that exists. Another result from a bunch of authors is that each of those integer programming instances can be solved in some time, which is exponential in the primal treedepth. Somehow the proximity bound appears, treedepth also appears, and the dependence in the number of variables is linear. So we just merge these two results together and we get what we want. Where into this PPA, we plug this expression here. So in the primal world, the result is very easy to obtain. So some remarks. This G prime here is triple exponential in the treedepth, primal treedepth, and there exists some evidence that this triple exponential is the best we can do. Dushan can tell you details afterwards. He can sketch some details afterwards. Okay, cool. So for the primal case, we are done. Okay, is that clear? So if that is clear, then let's look in the dual world. So in the dual case, the situation is much more complicated. Complication number one, there doesn't exist any nice result like the triple exponential thing. Okay, so we don't know if such a result exists, and there exists some evidence that this result actually cannot exist. In the dual world, you cannot have such a proximity bound. It is not like I don't think it's like conclusive yet, but there is very strong evidence that the proximity bound cannot exist. So is the talk done? It's not yet. So we don't give up, and let's try to re-examine the scaling algorithm, right? So again, in the scaling algorithm, you start with some sort of initial feasible solution. You look into some small box, and you search for a new solution inside the box. And the proximity bound, the triple exponential thing we use, is for this distance here, for the length of the box, the side of the box. And in the dual world, it seems that this length has to depend on n somehow, which might seem like a huge obstacle. But okay, so what is our idea here? Well, we'll be a bit less ambitious, and instead of descaling all variables at once, so instead of adding all the points between every two black points, we do it variable by variable. So first we densify only the x coordinate, and now we hope that there exists some sort of proximity bound, which we will show that exists, that we can use to jump to a new solution. And now we densify the second coordinate, and then we hope that again there exists some sort of proximity bound that will push me to the right solution. So if, for example, you know from approximation algorithms what iterative rounding is, this should be somehow you should see some resemblance. But instead of going to the dense lattice all at once, do it variable by variable, and we hope for the best. So the question is, we did hope, but did we get anything? And the answer is yes. So I will do some notation. So imagine you have some SIP instance, and now you have some subset of variables, capital I. And so the capital I scaled instance of integer programming basically means that for each variable that appears in this capital I go to the denser lattice. And for each variable that appears outside of this capital I'm still in the original sparse lattice. Okay. So some variables are now in SZ, and some variables remain in the lattice to SZ. That's what happens. And now, now with this piece of notation, the informal result, the informal proximity bound that we show is the following. So imagine you have integer programming, and now you densify some variables I, and also you densify some variables j. Okay, so you can do that. And now the question is, if I want to look for an optimum for this instance with denser variables I, and I look for a different optimal solution with these denser variables j, how far apart can they be from each other? And turns out that the bound is basically, again, some function of the parameters, so the largest coefficient and dual treedepth, times the difference of the size of the sets. Okay, so you cannot avoid that. But okay, so this is a mouthful. But what's the takeaway from us? The takeaway is that if these I and j differ by one variable, so I descale one variable and I have the original instance. So if I only descale one variable from the original instance, then the bound between the optima is 4 times some function of the dual treedepth and the largest coefficient. And again, this looks like a function of our parameters. So it looks like we have something to do here. Okay. So with this proximity bound in mind, we can proceed to the dual algorithm. So again, we will do the scaling. But in each iteration of the scaling, instead of descaling all variables at once, we do it a variable by variable. So, and by theorem 6, the one before, we know that if I start with an instant and now I densify one dimension, so one variable, then I know that the new optimum I'm looking for is at most this function of parameters away. So somehow I go look for it. Then I descale another variable, and I know that I need to walk at most this much away, this much to find a new optimum, and so on. So for dual algorithms, I mentioned it here than the primal, so I will be very light on the details. But basically, after descaling a variable, and I want to search for a new solution, and searching for this new solution leads to this problem called L1IP. And what is that? L1IP is the following. You have some initial feature with this x, and now you want to find a step h. So you want to write some vector h, which you follow to find a new optimum solution. So that's why we want a times h to be 0 vector, so that it remains a feasible solution. We want this x plus h to lie within the bounding box of the integer programming instance. And due to the theorem 6, which says that the change that we need to make is bounded in parameters, we require that this h in one norm is bounded by some row. And this row will be actually this, whatever is here. So now all we need to do is to solve this L1IP. So L1IP, I will just tell you that it can be solved in time which is proportional to this function here, times n, via dynamic programming. So basically, what you should imagine, you have your matrix, which is some sort of columns, right? So you have a bunch of columns of your matrix, and what you're looking for, and you want to assemble a linear combination of these columns that sums to 0. That's this part here. Somehow you need to lie within the box, the bounding box. Don't worry about that. But you know that you can use, like, the sum of the coefficients of your linear combination can be at most row. So you do some sort of dynamic programming where you basically do some sort of knapsack, or that's how you can imagine it. And it is easy to then imagine that if I told you it's a knapsack, that the dependence will be n times the biggest distance you can walk away from 0, or the largest coefficient you can use in the linear combination of the columns. Okay, so you can imagine that. So what would that mean, right? So it would mean that if I descale one variable and I look for a solution, and then I need a linear something linear times something FPT. I descale another variable, and then again I have to do something n times FPT, and so on. So if I do it naively like this, then I would need that the total time I would get would be quadratic in n, right? Because for each of those n variables, I need to solve a dp in time, which is again linear. So instead of doing this nice thing, we add some dynamization to the dynamic programming table. So basically, what we do, this is fit. So basically, we built a segment tree on the dynamic programming table, and in this segment tree, we can do updates quickly. Because what is an update? The update simply means we change the cost of using some column. So we propagate this this change of cost in the leaf root path in the segment tree, and from the segment tree we can somehow retrieve the optimum quickly. So since I mentioned the segment tree, what it means that now each searching for a new optimal solution can now be done in time log n times something FPT. And if I have n variables, then in total I will have dependence n log n for the variables, and then something nasty FPT, but we don't care about that for this talk. So that's what we did for the dual algorithm. Any questions? Yeah, so I mean, this is a very simple paper for local audience. You just do some DP and then you build a segment tree. I mean, there's nothing there's nothing interesting happening. Oh, and you add some knapsacks and from mathrm you bring proximity bonds and you're done basically, right? Okay. No, I mean there's some details that need to be that one needs to be quite careful about to make sure that the proximity bound works. But the ideas, it's a combination of known ideas, but you need to combine them in the right way. Yeah, and so maybe one historical remark as of 2022, actually, like these dynamizations are actually what leads to these near linear algorithms. Like if you, for example, have got a glimpse of what like these near linear algorithms for network flows do. I mean, you might not know what they do, but I can promise you that there's some sort of dynamic data structure which solves some sort of dynamization is actually at the core of these algorithms. So basically, if you want near linear algorithms, you better learn how to dynamize. So concluding remarks. So we also proved that our approach for dual algorithm, so this dynamic programming, and on top of which we built a segment tree, cannot be sped up, and we simply reduce sorting in a comparison model to this strange data structure. So there is no flaw in our analysis, is what I'm saying. Okay, I'm bragging here. I'm bragging here. Okay. So we conjecture again that the dependence on n in the running time of the dual algorithm is optimal, meaning that the log n cannot be avoided. We have some sort of evidence there, which I can tell Dusan, and Dusan can tell the rest. And so open problem. Open problem number one, get rid of log n. I mean, we have some indirect evidence, but it's like very indirect, and it's not right there yet. So maybe our approach is wrong, and maybe Dusan can invent something. Yes, but you need to decrease the number of indirections in a controlled way so that you don't stray away from them too much. Or the second direction would be actually you can take the information-theoretic lower bound and you can strengthen it somehow. Okay, so you can maybe you can reduce sorting to some sort of integer program and then hope for the best. Or maybe let's be a little less ambitious and let's just remove the local factor for some special cases of special cases. For example, instead of having separable convex functions in their full generality, maybe you only have separable quadratic functions. So in each variable we have a parabola, is how I imagine it. Maybe it helps, maybe it doesn't. But anyway, thank you for your attention. That's it. So questions? You can ask about dynamic programming too. I mean, I know. I can put it in the AG1 slides if you want.
So I was just wondering about the formulation of the IP. So it's I don't allow constraints like of the form AX less than equal to, right?
Yeah.
Only have like bounds on the coordinates, and then it's only AX equals B. So this is already a special case.
Yes, but I can, but you can do the usual adding of select variables, right?
Yes.
And then I can promise you that the treedepth increases by at most 1. Because, because in this, I mean, I'll do a picture. So you have this threefold matrix, right? And now you add, a bunch of 3 variables here, so you can basically kind of do something like this. And in the primal case, you get it for free. So, next question. Any solutions, maybe? I mean, I leave the open problems on the last slide always, so that I can hear some solutions. No solutions.
There are no solutions. Then I guess let's see the speaker again.